Hello, everybody. Can you hear me well? Online, I hope as well. So it's a pleasure for me to be here today to speak about SVOM after 2 years from its launch, and giving this talk, as Stéphane said, on behalf of the French PI of SVOM, that is Bertrand Cordier. So first of all, I will present you the consortium that is behind SVOM. So SVOM is a Sino-French mission. You can see here the laboratory and institute involved in China and the one involved in France. The PI ship is a CEA, and there's a large contribution of CNRS, and it involves the Chinese and French space agencies, of course. So this is just a bit of timeline. You don't see the titles. Sorry about that. So the launch has been more or less 2 years ago, and now we are in the phase of a scientific exploitation, and then with the nominal scientific operation that started in April last year. And in principle, the mission had a nominal duration of 3 years, but we are pretty confident of the +2 and maybe also another +2, since we had REVEX that worked very well with the Space Agency very recently. So this is the mission. There is no way to take away the... Sorry. Thanks a lot, Benjamin. So this is the mission, the SVOM mission. And very importantly, I want to stress that the SVOM mission has two components. The space part with the GRM and Eclair that detects gamma ray transient and gamma ray burst. MST, that is the X-ray instrument with the narrow field of view, and the visible telescope is the visible instrument to detect the counterpart of these transients. I will go a bit more in detail later on. But together with this space part, there is also a ground-based part that is also very, very important for the project. That is a kind of new component of the space mission dedicated to transients and gamma ray burst, to the gamma ray burst in particular. And so we have the GWAC, that is a kind of shallow but large field of view set of telescope. And then we have two instruments that are the Chinese and French ground-based follow-up telescopes that are really kind of dedicated to follow up all SVOM gamma ray burst, and plus some additional science that they do. Okay, so there will be a talk, it was because it was there will be a talk also on Friday, more specifically on the result of the French-Mexican ground-based follow-up telescope Colibri. So I invite all of you to go and listen to this talk if you want to know more about the very nice science that they are doing with this telescope. So more in general, if you want more information about SVOM and its instruments, its way of working, the science centers and so on, there is a special edition of SVOM that will appear on Research on Astronomy and Astrophysics, and you can already find the paper on archive. There is all a series of paper that have this reference, really that will give you a lot of detail of the aspects of the mission. And I want to point out also more recently, there are these two papers on the archive on the first results, the first science that has been done for the general program and for the gamma ray burst program. So I will not go, as I said, in detail instrument by instruments, but I would like to stress some specific things of SVOM compared to past and present missions focused on gamma ray burst and transient science. So focusing, starting from the space segment. So here you have the comparison of the capability in terms of domain of frequency spread of SVOM instruments and of other missions like Einstein Probe, SWIFT, Fermi, and GECO-LAM. So here I want to stress a couple of things. First is the VT. So this visible telescope is really a new thing in this science domain. We had SWIFT that has the UVOT, but the advantage of having the visible telescope on board is that it spread a much larger, let's say, much larger towards the near infrared domain of wavelengths. So it goes from 400 nanometers to 900 nanometers. And it's much more sensitive than UVOT. So that means that we can detect the counterpart of the gamma ray burst much more frequently than what UVOT could do because of its less sensitivity and also being more sensitive in the visible and ultraviolet to the problem of dust extinction not allowing to detect the GRB's counterparts. The other thing that I want to stress is the fact that we have the two gamma ray instruments, Eclair and GRM, that allows for gamma ray burst, for example, to study very well the spectral energy of the gamma ray burst, going very well, being able to determine, for example, the energy peak. And also I would like to stress that the frequencies where Eclair is sensitive are exactly at the end of the frequencies where Einstein Probe WXT is sensitive. So there is really a big interest of these two missions to do together some science, because they can really, if they join together their capabilities, they can cover really a large frequency domains for the transients event that they are studying. And I think there will be a talk today, later on, by Dean and Adrienne, stressing really the science in synergy of Einstein Probe and SVOM for transients, and GRB in particular. So now I want to focus also on other aspects, not only on the space part of SVOM, but the space part in collaboration with other missions and the ground-based part. So first of all, we have an ongoing, very rich collaboration with Einstein Probe and SWIFT. So every time that we have a GRB detected by SVOM, Einstein Probe will go and look for with this instrument to see if it detects the burst and the counterparts. And the same was true with SWIFT when SWIFT was operational, and we really hope that it will be soon again. And it also is vice versa, is true. If there is an Einstein Probe event, we go and look for the counterpart with SVOM instruments. Then another very important aspect is this ground-based segment. So as I told you, we have dedicated facilities ground-based, so that, as I show you here, the French, Mexican, and the Chinese follow-up telescope, for example, but we have very strict collaboration and partnership with other telescopes on ground, so that at the end we have kind of a dedicated ground-based follow-up segment from the small telescope to the biggest one. So we have time both on the LCO, and we have a close collaboration with the NOT. Daniele Malesani is here representing this collaboration, and not only, but also this. And then we are also collaborating with the Stargate collaboration that has the large large program to follow up GRB with the ESO VLT telescope. And there is also, here is not shown, a partner, let's say not a partnership, but a very useful and efficient collaboration with the Grand Tecan telescope on Carani Island, and Antonio is here, that is leading this project, also part of SVOM, and is also part of SVOM. So in addition to this, we also have, we are in contact with people that have programs in the radio, with radio facilities, and at very high energies, and there are already ongoing papers using also these frequencies to study SVOM gamma ray burst. So now, what is the point strategy of SVOM? SVOM has the characteristic of having a pointing load that is avoiding the galactic plane, so as to increase the possibility to perform an efficient follow-up of gamma ray burst, and also as an anti-solar pointing to optimize the follow-up. So all the mission, as you can see, has been really done to optimize the follow-up from the beginning. It has been thought like that. The disadvantage of this is that we have the Earth in the field of view every hour practically. So there are, sometimes is idle, the satellite. So then we have different scientific programs. You can see here what are the fraction on each programs that we have as base for the nominal mission duration, and then what we thought it would be the case in the extended mission duration. So we have a core program that is the one that is dedicated on gamma ray burst detection and high energy transients. And this program is the one that allows also an automatic slew when eclairs detect a gamma ray transients. Then we have a general program, and this is a program that is observing sources that are granting through a call for proposals. There is a new call that will come out very soon for next year. And this call, let's say, if you have interest in objects or things that you want to follow, is possible to participate, let's say, to this call if you include a SVOM COI. So if you have some observation that you think, for which you think the SVOM would be useful, please contact the SVOM COI and we will see. Then we have also a target of opportunity program. And this is divided in three different kind of TOs, the nominal, the exceptional, and the multi-messenger. Each of them has a different priority and speed, say quickness in being accepted, approved, and uploaded and executed. And I will also maybe emphasize later on, these TOs exceptional nowadays are extremely fast because we use the Chinese satellite system to trigger them, and this is also the one that we use to follow up, for example, GRB that we detected, to keep following them up, or to follow up GRBs detected from Einstein Probe, for example. So this is a typical alert sequence for a GRB event. So from T0, then the alert emission, repointing, MXT, so the X-ray instruments that observe the regions and gives a preliminary position. Then we have a position from the visible telescope a bit later on, and we have a sequence that ends after more or less 8 hours from the triggers. We have different ways of communicating data to the ground. So, and uploading also. So as I said, one is Beidou, that is the Chinese satellite system. Then we have the kind of normal X-band and S-band to download all the data. And these are, they say, we can do it every more or less 6 hours. And then we have this system of VHF antenna that are spread more or less everywhere in the world that allows us to download a very small amount of information, but this is the information that we need to look at the data immediately and to say, okay, this is a good trigger, and also, for example, to look for the position in MXT or in the visible telescope. But this is very, very reduced amount of data. So what about the data? So I know that in this aspect, our community is used to Swift, and that is a very open data policy. For this new mission is not exactly the case. So we will have a GRB products that will be public to all the community from this autumn. Starting from the Eclair and GRM products, and then also the one of the other instruments. There are ongoing work to deliver the first GRB and general program catalogs, always on Eclair and GRM instruments, and then ideally this will be released every year. And then you can also access the data, the products, let's say, if you have projects that you submit to SVOM people and that are done with a SVOM COI. So we have, for example, in gamma ray burst, we have 3 different type of projects, usually one that is entirely on SVOM, the type 2 that is means that is led by SVOM but has external collaborators, and the type 3 that is led by the external collaborators with SVOM participations. So we are working like that, and we're already working in collaborating with people external from the community that is outside SVOM. So, as was mentioned by Stefan already, it's 2 years that SVOM has been launched. So I have a bit of statistics to show you. This is the pointing of the SVOM second year of orbit. So more or less, these are the statistics that kind of reproduce what we expected by the time share between general program, GRB observation, and target of opportunities. Yeah, I don't have much more to say. This is a plot where you see all the triggers of the 2 years, so since launch. And you have in terms of long GRB, short GRBs, X-refractory reach. In yellow, you have all those triggers that are not gamma ray burst. So you can see a bit what we are observing. And so in total, in these 2 years, we detected more than 400 transients by eclair or GRM, or in combination of the two, and 318 are gamma ray burst. And here I show the distribution what are not gamma ray burst. So the sources that trigger eclairs, but not being gamma ray burst. And so you can see that we can do really also very different kind of science on different kind of sources, also beyond gamma ray burst science. The papers, that is the way that you have nowadays to have access to what we see, except for ALERT and GCN, of course. So we have 6 papers published on GRBs, plus 2 submitted, and we have a lot in preparation that we really hope to be able to release soon. There is really very interesting science, I also think, especially for theoreticians. And then this is the situation for the general program with 9 papers published, 2 submitted, and 15 in preparation. I show you some example of the general program. This is not my science, so I will just show you some example, but I'm not the expert on this. So here I show you some results on low-mass X-ray binaries detected by SVOM, and you have the papers where you can find all the information of what SVOM is detecting and the importance of the results. And then here is, I show you a couple of examples of blazars observation. But for example, for the general program, you're also monitoring sources like, for example, Sinus X3 and so on. So then to go to gamma ray burst science, this is the number of GRBs that we detected by eclair, almost 100, and the other and the intersection also with GRMs. So this is a bit of statistics also to refer, for example, to compare, for those of you that knows, to the statistic of Swift, for example. So as you see, we have maybe lower number of GRBs for which we have an X-ray detection. This is also due to the fact that the X-ray instruments is less performant than for example, of Swift XRT, is less sensitive. But we work together with Swift and Einstein Probe, as I told you, and this helps a lot. And the fact here, this fraction is also affected to the fact that Swift is missing now on the panorama of our science. What is really amazing is that we have a very high fraction of gamma ray burst with the optical counterpart detection. This is very, this is kind of different from what we are used to, and this is really due thanks to the follow-up systems that is taught since the beginning, and thanks to the Visit Pulse telescope and the ground-based follow-up telescope, the French, Mexican, and the Chinese, especially. And we have a high fraction of GRB we actually measure that is 40%. So Swift are less than 30. So this is very important because, of course, when we have a redshift, we can multiply the way of making science with what we observe. So I want to stress as some of the some of the interesting results that we are finding with SVOM. The first concern the optical counterparts. So here I show the revolution that has been brought by Swift on the X-ray counterpart of gamma ray burst. So this is the idea that we had of an X-ray counterpart of a gamma ray burst before Swift. And this is what Swift showed us, so that the X-ray light curve of the GRB afterglow was really much more complex than we thought theoretically. And in fact, with SVOM, we are seeing similar things for the optical light curve counterpart. So nowadays we have the idea that the X-ray is complex, but the optical more or less is this, or maybe you have a bump here and there. And instead, we are really seeing a complete a huge scenario of different cases of optical counterparts. And I show you maybe one of the best examples that we have of these complex light curves. So this is the visible afterglow counterpart of this gamma ray burst of 2025. And this is the light curve has been followed by the visible telescope and by the French-Mexican ground-based follow-up telescope Colibri, plus LCO and the Grama collaboration. And you can see this is not at all what we expect as an optical counterpart. And you can see these huge bumps at late times and steep decays and then bumps again. So I think that for the people that are that likes GRB physics and GRB modeling, we have a lot of data that are really very interesting to be interpreted. Then another very interesting result and great result for us that we had in these 2 years of operation was the detection of the gamma ray burst at redshift 7.3, this one, 250314A. This is the fifth farther gamma ray burst, but what is interesting here, you can see from the GRB names, it has that it was a while since we didn't detect a GRB a very high redshift. So this testified really of the SVOM capabilities to detect this high redshift gamma ray burst, and also is really a success of the collaboration with all the partners and collaborators for the ground-based follow-up. Very importantly, for this event, we have this tentative detection that I hope will be confirmed with further GWST observation that we will have, of the supernova, very similar to the 98 BW, like supernova associated with gamma ray burst. So this is the further supernova that has been ever observed to date. I want to show you here that for this science, what is really key is the near-infrared imaging and spectroscopy, and that still we are limited by the lack of instrumentations that provides near-infrared imaging spectroscopy sensitive enough. So we have just a few facilities that can perform this, and we have many other cases, as you can see here, or very deep early time limits provided mostly by the VT telescope on board of SVOM for SVOM GRBs. And so, in principle, among these, there are also other candidate high redshift gamma ray burst, or other interesting, in any case, cases of gamma ray burst, dust extinguished or very faint, or so on. And we really hope that there is this new instrument that should go on the Colibri telescope that will observe the near-infrared counterpart of SVOM gamma ray burst, and we really think it will help in this exercise. Okay, then I just mentioned other cases that are interesting. So the fact that we have all these instruments working together that allows really to analyze the spectral energy distribution on gamma ray burst over a very large frequency range. And also we have cases like this one where eclairs trigger on the afterglow on the gamma ray burst, and this is also very interesting for GRB science. Then I want to conclude this part on the GRB, let's say, interesting result that we are having on the exploration of a new parameter space in the GRB EPK ISO range, parameter space, let's say. So this is the usual GRBs, the long GRBs that are detected usually also by past mission and so on. And as you know, also with Einstein Probe, we are now probing a bit more this area. But with SVOM, we are really pushing also the exploration of this part of the plot where we have low E peak but quite high energies, isotropic energies of the burst. And furthermore, with SVOM really having also the access to the Eclair and GRM also at high energies, we can really have constrained very well the peak energy of the burst, and so being able to characterize the population much better than before. And here I just show you plots from a paper of Benjamin Schneider that will give you a talk tomorrow on one of these events. So this seems to be a kind of more one of these X-ray flash, but with normal counterparts in a sense, but Benjamin will tell you more. And this is in another example where we have a completely different pictures. This is much higher redshift. And here we have this X-ray and optical light curve. The optical light curve is very strange, and there are different explanations that are proposed. And maybe it's structure, we can probe the structure of the circumstellar medium of the GRB. There is a paper in preparation how soon, so, but I want to stress the diversity of this X-ray flash population. And then last slide on science is on CATCH. That is a mission that we are preparing, not really after SVOM, but we hope within SVOM. So this is a constellation of satellites that is planned by China, again, with within which France is contributing. And in particular, it's contributing to this precursor mission. This is a kind of demonstrators for which we will have a gamma ray satellite that communicate with an X-ray satellite and an infrared satellite. So the idea is that both this Scout satellite and SVOM can detect gamma ray burst, and then the follow-up can be done by SVOM, but also by these other two satellites. This is kind of properties like WXT detectors, and we have also this infrared satellite that we hope will allow us to detect the counterpart of high redshift gamma ray burst. And this is my last slide, just to advertise that we are hiring in the Paris area. In particular, we have 3 postdocs positions that are open to work or with myself or with Émeric Lefroc at CEA on SVOM GRB science and on GRB galaxies. So if you're interested, please just come and talk to me during this week. I will be very happy to tell you more about this. Thanks a lot.
Okay, thank you. Thank you, Susana. We have time for very few questions. No.
Yeah, thank you very much. Nice talk. And yeah, maybe I should wait until Friday talk, but you commented redshift 7.3 is the highest. So how is the other? The distribution is something similar to Swift, or?
For the moment, yes. Let's say more or less is similar. So we are a peak around 1, 2, and going then down towards 6. Yeah.
Okay, thank you.
One other question?
Just a clarification, hi Susana, on the data release policy. So is the high energy data going to be released in real time, or is this just going to be a release of the data for the first few years of the mission retroactively?
So the raw data will be never released, to my knowledge. What will be released are the data products that will be released from the autumn. Let's say what we think is that in every GCN you will have a link where you can click and look at the real-time product of the high energy instruments. Then to have access to the data, this is through the projects. If you have a project that you want to do, for which you think you need SVOM data, you can contact or the GP program leader, that is Alexis Colero, or the SVOM of the GRB program leader, that in France is Frédéric Daigne over there. And you kind of submit your idea, your project, and then this is discussed within the group to see how to have you carrying out this project with SVOM people. Is it correct, Frédéric?
Okay, if you want to keep the schedule, we can thank you again, Susana. You want this? And now we host Nicole Mulyk. And I let you have 15 minutes.
Perfect. Thank you so much. Sounds good. Okay. Hello, everyone. My name is Nicole Mulyk, and I'm a PhD candidate at McGill University. And today I'll be here speaking on behalf of the CHIME FRB collaboration to talk about our upcoming baseband catalog that'll be released in fall 2026. And I'm also going to talk a little bit about the research that I've been doing with this catalog as well. There we go. Okay, perfect. Thank you. Okay, so as a member of CHIME FRB, I primarily work with fast radio bursts with FRBs. These are very short duration, very energetic bursts that we can only detect in the radio. And they're really just a big mystery in astronomy right now. We don't know what produces them, and we don't really know how they're produced. And what makes it really interesting is that while most FRBs seem to be one-off emissions, we do see about 3% repeats. So we don't understand whether or not these repeaters and one-off events are the same source. We also know that they're extragalactic in origin. We know this because we can measure the dispersion of the FRB burst. So we see this sort of sweep here in the famous Lorimer burst. And this sweep decrease in frequency is caused by dispersion, the interaction of the light with material. And so, like I said before, FRBs are really just a big mystery. We don't understand what produces them, what their progenitor are, what their emission mechanism that produces them. Maybe are repeaters and one-off events the same progenitor or emission, and whether or not all FRBs are capable of repeating. And so these are kind of the questions that I'm trying to answer, particularly looking at the FRB environments and how they interact with them. All right, so I already mentioned dispersion really quickly, but I'm going to dig into it a little bit more deeply. So the FRB itself is emitted in some host galaxy, and as the light travels to us, it has to move out of the host galaxy, through the intergalactic medium and into the Milky Way. And all through this journey, it's interacting with material. And so we measure this with the dispersion measure, which is proportional to the distance that the light has traveled and the number density of electrons, or basically how much material that light has to interact with. And so by measuring this, we can tell that they're extragalactic. And so with CHIME, the Canadian Hydrogen Intensity Mapping Experiment, we are detecting thousands of FRB bursts per year. You can see in the plot on the top, this is a logarithmic plot that when CHIME began observing in 2018, the number of FRBs detected increased substantially. And this is because CHIME has a large field of view and it observes the entire night sky every day. So CHIME is a stationary telescope, and the way that it does this is that as the Earth rotates, the entire sky kind of panels over it, we're able to observe it. And so it does this also at a very high time resolution. I'm going to talk a little bit about that time resolution, how important it is. So CHIME is continually collecting total intensity data, which is then fed into a real-time pipeline that looks for FRBs. And if we detect one that's significantly bright, we save the complex voltage or baseband data. We don't save this for every event because this data is immense. It carries a lot of information. So it has a significantly higher time resolution, but it also carries the phase of the radio wave and the polarization information. And so just to give you an idea of how much better this data is, on the left, we have the intensity data, and on the right, we have the exact same burst and baseband. And you can see the complex structure that appears once we have that high time resolution. So what's actually going to be in this BaseCat 2 or baseband catalog 2? This will include all FRBs that we have baseband data from CHIME reported since the beginning of when CHIME launched up into September 15th, 2023. And because of this long baseline, it's going to have over 2,000 bursts. So this is an immensely large catalog, including 73 repeaters at that high maximum time resolution that I mentioned. So the benefits of having a really large high resolution catalog is that we're able to determine the burst properties with a very high degree of certainty. This includes things like sub-arc minute precision in our localizations and potentially even host galaxy identifications. We'll have polarization information and lots of other data products. But I just really want to emphasize that this is 15 times larger than our previous baseband catalog. So it's got an immense amount of information ready to go to do some interesting science with. So the science that I'm particularly doing is trying to answer that question of, do we understand how FRBs are created? And the way that we do that is by looking at their environments. So I'm going to revisit this idea here. So like I said before, we're looking at how much material that light passes through, and we can measure that. And now if we assume that that distance it travels is relatively constant, if we see variation in the DM, specifically here on a time scale of months, what could be causing that? Well, if the distance isn't really changing on any kind of time scale of months, then it must be a change in that electron density. And since we're seeing that evolution on a time scale of months, we really can't expect that to happen in the Milky Way or the intergalactic medium. We would expect evolution in those regions to be on longer time scales. And so this really tells us that we are probing the regions directly surrounding the FRB itself. And so what could be causing changes in the electron density in the direct region related to the FRB? Well, in general, we think that this is due to inhomogeneous or turbulent plasma. There's several kind of models in the literature, including things like expanding supernova remnants and magnetar wind nebula. And so the main goal of my project is to measure these changes as we can with FRBs in the magno-ionic plasma. The great thing about repeaters is that we observe them multiple times, so we can see how these properties change with time. And fortunately, we've been observing many of these repeaters for years. So we have a very long baseline to do this for. And many of these cases in the literature will study like one or two or a small handful of repeaters, but we'll really be able to do a large sample with this. Like I said, BaseCat2 has 73 repeaters. And so far, I've eliminated down to 50 that have, at least a few measurements where we're very confident in the dispersion measure. So really the question that we're trying to answer is, can we understand the FRB progenitor by looking at its environment? So I've teased this plot that's sitting here on the right for a few slides now, and now I'm going to kind of dig into it. And this is an example where we can actually see the dispersion measure changing with time. So this is one repeater and all of its bursts, and they're organized chronologically, left to right and then top to bottom. And you can actually see it changing with time. So if I had correctly dedispersed each of these events to their correct DM, you would see a vertical line. However, what I did instead was dedispersed each of these events to an average DM. And so you can see how that changes. So on the plot on the left, you can see a horizontal line. That's the average DM that I dedispersed to. And you can see where their actual DMs sit along that line. So initially, when we're in the top left region, it's over dedispersed. So it's sweeping to the left. And then you can see with time, it sort of straightens out and becomes, close to the average DM, and then starts sweeping to the right where it's under dedispersed. So you have several examples like this in our sample where we actually see this changing DM. And this agrees with what already exists in the literature. So it's very well established that a decreasing DM can be observed for repeaters. There's lots of examples of this in the literature, but there's only a few of increasing DM. And we have both samples in our sample as well. And with these examples here, the initial test that we've done is looking whether we're likely to have stochastic variation, and neither or both of these came out as being unlikely to have stochastic variation. And we have sort of a trend that looks like it might be linearly increasing or decreasing, but we've only just done this initial test with a linear trend. We do intend to do a little bit more complex fitting. And so 80% of our sample currently sit in the range of probably need something more complex. Quite a few of those just look like they appear to be constant, and so likely we'll present them that way. But there are a few that seem to have unlinear trends that we're going to focus on next. But of the 20% that we're fairly confident with, 17 of those are decreasing and 4% are increasing, which agrees with the literature, having many more examples that are decreasing than increasing. Yeah, so I'm just going to end with letting you know that you should keep an eye out for these upcoming papers. So BaseCat 2, excuse me, and my work looking at FRB environments will both come out in fall 2026. And I just want to acknowledge that all the BaseCat 2 work was done by this great group of people who've worked very hard over the last couple of years to get it ready, especially Caitlin Shin, who led the project. Thank you, and I can take questions.
Thanks. This was a really nice talk, very clear. And you mentioned a couple of possible environments in which these FRBs can happen. You mentioned expanding supernova remnants, magnetars with nebulae. Do you have any one-to-one comparison between these FRBs, like the way the DM changes, and galactic sources? And is there anyone that tracks particularly well?
Yeah, so that work is still being done, but I'm hoping to have that as part of the project. The CHIME outriggers are now online as well, so we're hoping to get some localizations from them as well and be able to cross-reference with host galaxies to see if we see any trends in our sample that we can then trace back to their host galaxies. So I guess the answer is not yet, but soon.
Any other question, comment?
Thank you for your nice talk. I'm a little worried looking at the delta DMs that you showed. They're very small and not even a factor of 2. And given L is fixed, right, the density change could be just minuscule. So I don't know how much will you be able to understand about the environment. I mean, perhaps a different measure would be looking at rotation measures to probe the nearby environment.
Yeah, so I didn't present it here because it's still in its early stages, but I'm currently working on rotation measure and scattering time scale. And so we'll look at the correlation of all three to try to really understand what's going on.
Thanks.
Okay, thank you. Thanks again to Nicole. Okay. The third speaker is Mathieu de Bony de Lavergne. And I have to change the slides. Okay. Will work. So you have 15 minutes.
Okay. Thanks a lot. So hello everyone, I'm Mathieu de Bony, I'm postdoc at CPPM, but in here I'm today more as transient convener of the LST1 collaboration. So I will present you quickly what we do in terms of transient science in LST1. So first, quick look at the instruments. So LST1 is part of the CTAO project, so the Cherenkov Telescope Array Observatory, which aim to have the best EACT system. So we detect very high energy gamma rays by looking at the Cherenkov lights emitting during showers created by those gamma rays. And so the LSTs are the biggest telescope of the CTAO system. And so here you see the first one, and you see also the next 3 ones who are currently being built. And And so we have a 23-meter diameter reflector here, so very large to catch a faint light from the showers, with a camera of 1815 PMTs. And the interest of LST is to be able to go much lower in energy, down to 20 GeV, thanks to their very large mirrors, which make it really great for transient science. It has also ability to reposition in 20 seconds nearly everywhere in the sky. So this is really gigantic machine. So this is really interesting. And we have also a quite large field of view, around 5 degrees. And really the nice thing with LST, we could go to energy similar to the high energy part of Fermilab with much, much better sensitivity on short time scale. So in LST, we have a lot of systems to help us and procedure on transient science. So first, we have a transient handler, which is running since 2020 for receiving and processing the alerts. And with this, we are able to automatically react to GRB or GW alerts for fast follow-ups. So combined with the very fast repointing, and meaning in the best case, we could be in 40, 50 seconds on target after the trigger. And we have also automatic tiling for alerts with large localization uncertainty. So this includes GWs, but also Fermi GBM alerts. And so this is also with automatic repointing. So even if we have large uncertainty, we could try to probe the best localization very fast and continue automatically exploring the different possibilities with different pointing. Then we have a real-time analysis to get quite fast results as soon as possible. But we have also next day analysis performed by a dedicated team to get more detailed insights the next day. And in the most relevant case, we are making some fast communication to the communities through GCN, ATOL, astronauts, based on the result of this RTA and NDA. But it's really a case-by-case communication. It's not yet really standard. So if we go a bit about the main results we got currently, the first one I want to present is the observation of the boats 221009A. Where we started observation 1.3 days after the burst. So it's quite high delay, but the boat decided to explode during full moon. So this is really a big issue for EACTs. It was not even planned to operate the night where we observed. We have to ask shift crew to go on site earlier, a day earlier. And we have to change the camera settings just to not burn the camera on the sky. Observing this. So, really a big achievement to get this data and be able to analyze them. And so in total, we observed for 16 nights, not all the night, but across 16 nights for 13 hours of observation. And the interesting part is we got a hint of emission for the first night of observation. So if you look at the light curve, so here most of the data is from LASSO, but here you have the EACT constraint. So in red you have the S, and in gray the LST one. And so we could see here the first night with the flux, we get this hint of excess, which is quite in agreement with some of the Afterglow model. So if you want more detail, you have the publication here. Second, we observed quite some events with O4. We didn't get very lucky on the BNS side of things, but O4 gets some very well localized binary black hole event, at least for comparing to the size of our field of view, which allows us to observe it with a single pointing, which allows us to spend all our time on this, so much deeper constraint than what could be done usually. What is interesting is for one of these two events, there are subthreshold detection for swift bars. And this observation were also done jointly with MAGIC, which is a telescope, two telescope system, EACT, which is just very close to LST1. And so we could observe together to try to improve sensitivity. So observation delay is relatively high, but it still allows us to get some nice observation of the full region, and also to derive some overall upper limits for the emission of the BBH. And so flux upper limit map and global flux upper limit like this will be included in the final publication, which has been submitted to the journal, so should arrive hopefully not too long. And there are some constraints on emission scenario of binary black hole in accretion disk or AGN disk included in this publication. Next, we go to supernova. So this is one of the supernova observed with LST1. So it's a type 2 NL supernova at 20 megaparsec, so quite close. And in total, there are 15 hours of observation spread from 16 to 38 days after the explosion. So we didn't get any detection, but we still have some constraint. And this is the lowest energy threshold for a supernova observed at very high energy, which is quite interesting because quite a lot of models predict some significant absorption, which will depend on the time, but the lower you go at energy, the less absorption you should have. And this is also the first type 2 NL supernova observed at very high energies. And we have some very also analyzed archival Hubble Space Telescope data, which hint at a red supergiant progenitor. And finally, with the very high energy data, we were able to constrain on the mass loss rate of the progenitor. And if you want more details, the publication is here. And if we move to TDE, so we recently observed the first TDE with LST1 jointly with MAGIC. So this is one quite close by, 0.01 for the redshift. And in total, 30 hours of observation from November 25 to February 26 were taken. And it was the occasion to send the first astronauts for LST1, giving a bit insight on the first night. But more detailed results will be shown later this year. So if you follow Gamma conference or TEFPA conference, you should have more information on the detail of this result and also modelization to perform with the help of very high energy observation. And finally, I choose to present a galactic source, but why this one? Because it's associated with an FRB, so I thought it might still interest some of you. This is the soft gamma repeater 1935 plus 2154. And so we observe it in total 31 hours between 21 and 2022. And the interesting part is we got 9 X-ray bursts within our LST1 observations. And so this allowed us to be the first to have direct, very high energy upper limits on soft gamma ray repeater bursts. And as you could see on this figure here, we don't have detection, but we have very constraining upper limits. We are order of magnitude below the flux at MeV. Which allow to constrain quite a lot of things. And we have also the most constraining upper limits on persistent emission for the region. But yes, sadly, no detection either for persistent or burst. And if you want more detail, publication is here. Finally, I will not have time to go deeply over all what we are doing in transients, but I just want to mention that we are also observing fast radio bursts, neutrino alerts, AGN flares. So I've put you here on AGN flares two papers, one with intra-night variability and one where we have the highest redshift AGN detected at very high energies. A paper also on detection of RSO-Puki, so the first novae detected at very high energies. So together with MAGIC and HAS, we are observing also stellar flares and plenty of other transient phenomena. So we have an active transient program covering a large panel of scientific subjects. So multiple publications are in preparation. I didn't show all of them here because some are not yet announced. The low energy threshold and high sensitivity of LST1 really make a really great instrument to observe transient source at very high energies. And with the completion of the full 4LST array, it will really boost the performance. We'll have nearly CTAO, full CTAO performance for transients. And so the inauguration of these 3 telescopes is planned on the 15th of October. And finally, I want just to show you, here you have the corresponding author of all the projects I've shown you. But I've also put all the name of people with direct technical contribution to transient activity, because without all these people here, most of the study would not have been possible. And also there are more general contribution to the development of analysis tool, telescope systems, schedulers. I couldn't put everything here, just to insist that this work is really a large collaboration work of many people. Thanks.
Thank you very much. Time for a few questions.
Thank you very much for a nice talk. I was curious about the high energy emission or very high energy emission from the magnetaries. Do you expect it, like in, let's say, a TeV, or because is it not, the photons are not destroyed by some photon splitting effects or something like that?
Okay, it's quite uncertain. To my understanding, there are not a lot of models who really go up to this energy. So it really depends on the scenario and hypothesis you put, and there are really a lot of uncertainty here.
Yeah. Yeah, about supernova, you say something high energy emission can constrain mass loss rate. What are you assuming?
Yeah, because basically the more the progenitor has lose mass before, the denser will be the CSM around the supernova, and so the more potential you have to have strong shocks, so particle acceleration, and so very high energy emission.
Possibly you need to assume various things.
Yeah, I know they have to make quite a few assumptions. I don't know very well by heart like this, but it's all detailed in the paper. No, even for large uncertainty, it's fully automatized. So it's really, we receive the alerts and then we detect it's too large to get one pointing. So it's sent to a software which is called TilePile. And with TilePile, we get an automatic pointing strategy. So this takes a few more seconds, obviously. And then based on this pointing strategy, we automatically point the telescope to the most probable location, and it's automatically scheduled also all the other observations. So there are really no human in the loop. For shifters, it's usually a bit disturbing because they are here and suddenly a huge noise because the telescope starts moving and stuff. It's really a full building who is moving here. It's really a...